All right, so today, not doing that, we are talking about inodes, which are the final journey of our file system. So this is what's actually used on Linux and Unix, and it's a lot of fun, and you will see that all your page table knowledge is applicable. So yay, that wasn't a waste. So this is what an inode is. So an inode stores everything about the contents of a file, its permissions, who owns it, et cetera, et cetera. So all that information is stored on something called an inode. So the inode will store the mode, which are like the read, write, execute permissions for your file. It will also share which owners are in it, so what user owns the file and what group owns the file. Timestamps, so when was this file created, accessed, and modified last, so written to, which it's just sitting in an inode, so that's why no one trusts your timestamps on a file, because you can just modify it. You just write out some new timestamp. So that's typically why profs that know better will not accept it. I think, yeah, some friends of mine tried to pull that, like submit a assignment super late and then change the timestamp to before when it was due. So you can do that because it's just a field there. Yeah.
Did it work?
Did it work? I will not disclose that. So would it work in this class? Probably not. Would it work in some other class? Yeah, but sorry, you are in ECE, so you probably won't be able to take benefit of that. So other things it stores are how many blocks the file uses, and then the rest of it is kind of the same idea of that indexed allocation. So there will be a bunch of pointers to blocks contained within the inode. So there'll be a lot of direct blocks, so they will point directly to a block on the disk, and there are a lot of them to represent a single, like, small file. So remember when we had index allocation, we put all the pointers on a block, so we could store up to like 2 to the 11 pointers. Well, if all our files are kind of small and only take like 6 blocks, we don't really want to take a disk block to keep track of all the pointers when there's not that many we have to keep track of anyways. So inodes will have a few pointers there that point directly to a block, so you don't have to allocate a block just for pointers. And then the single indirect, so there'll be a pointer that represents a single indirect indexed allocation. So that will be the indexed allocation we saw before. So that will point to a block on the disk, and all that block on the disk has is a bunch of pointers that represent the other blocks that that file actually contains, which is exactly like index allocation, which kind of had the idea from page tables. So unlike page tables where you just have 3 levels and then we have to go through 3 levels, well, with inodes, we have a variable number of levels. So that single indirect one will go through 1 level, and then you can think of the double indirect one as a page table with 2 levels. So if you access that root pointer for the double indirect, it means you're going to go through 2 tables. So that pointer will point to a block full of pointers. So there can be 2 to the 11 of them, and then each of those points to another block that are full of pointers, and then all of those point to the actual blocks. And then to support massive files, there's also a triple indirect, so that will just do exactly like page tables do for 3 levels. So why they do that is so that they can be efficient for small files and also support large files. You don't want to, if a file is only like a few bytes, you don't want to just do everything triple indirect. In that case, even if your file is like 2 bytes, you're going to waste 1 block for level 2, 1 block for level 1, 1 block for level 0, and then a block for the actual contents of the file, which would be like 2 bytes out of like 8 kilobytes maybe. So you would be wasting, what's that, like 32 kilobytes on like an 8-byte file or something like that, which would be absolutely terrible. So that's why there's the direct pointer. So if it's small, it doesn't even allocate a block for all the pointers. And then if you have larger files, it scales up, so it only uses the number of levels that it actually needs to represent the file. And there's a caveat here that we'll see that very small files can actually store its content directly in the inode itself, which we'll see what that optimization looks like.
So
yep.
In this case, like those small files will be stored in direct blocks?
Yep. So in this case, say you have a small file that only takes up 2 blocks. So say the first block of the file is like block, I don't know, 1,000, and the next block is 2,000. Well, in the direct blocks, the first index there, index 0, would be block 1,000, and then index 1 would be block 2,000. So it'd point directly to it.
Okay, and it's single indirect, double indirect, will those always be there? Like, will that second always be in the inode?
So those will always be in the inode, but they're one pointer. So if it's a small file, they'll just be null.
Okay, so, and then triple indirect is also always in there, but it's just not used?
Yeah, so triple indirect is there. So if it's valid, like if it's a pointer to a block, then you know you have to hop through 3 things, but it can just not be used.
Okay, so like,
So,
if you want to look for data, you just have to look for all of these?
yeah, so you access these in order. So like the first few blocks of the file would be direct, and then the next, after the direct blocks are out, it would start filling it up single indirect, and then if that's all filled up, it would go to double indirect and then triple if it needs to. So it would fill it in order because the more levels we have too, the longer it's going to take to access it because we still have to jump all the levels. So we just use them in order. So small files, we just look directly, and the smaller optimization is we can actually cheat a little bit and store it in there. Yeah.
Where exactly is like the inode itself? Is it just like saved on some page somewhere, or does it take multiple pages?
So the inode itself will also be on disk. So there's going to be a part of the disk that just stores inodes. Okay. And that will be allocated with like a slab allocator. So there'll be a bitmap for inodes, and there'll be a pool of inodes that you can take and use. So that will also be on the disk. Yep.
So it's like one inode per directory or one inode per...
So we'll see. We'll start making stuff and screwing around with stuff. But essentially, it's the contents of a file are an inode. And names are merely an illusion. We'll see.
Sorry, are those like, you said they're similar to page tables,
Yeah, so instead of a page, it's a block now on the disk.
okay.
So other than that, it behaves the exact same way. And it's the same idea where we fit as many pointers as we can on a block. Yep.
Yeah, so that single indirect and double indirect is pretty much exactly the same scheme that you saw yesterday, right? For index allocation.
So the single indirect is exactly what we saw yesterday, just one block. And then double indirect is just like the page table. So there'll be one block full of pointers, and if you follow a pointer, it's just to another block full of pointers, and you're supposed to follow it again. So instead of taking 1 hop, you take 2. And then for triple indirect, you take 3 hops instead of 2 or 1 or 2. Okay, so let's see, because we saw how big our file could be before with just essentially a single indirect. So our maximum file size could only be like, what is it, 16 megabytes. So let's assume we have an inode now and see how big of a file we can support. So in an inode, this is going to be the numbers that are actually used in Linux. It could move if you create your own kernel or something like that, but these are generally the numbers for an inode. So it will have 12 direct pointers, one single indirect pointer, 1 double, and 1 triple. So in total, there will be 15 pointers. And then our disk block size would be 8 kilobytes again, so we'll use the same numbers from last lecture. And a pointer again is going to be 4 bytes. So, and I'm assuming nothing else is on the indirect blocks, they just contain pointers. So now we can calculate the maximum file size managed by this block. So we know that each of the blocks can contain 2 to the 11 pointers. So using that, so here's our 2 to the 11. So each block size is 2 to the 13, and a pointer is 4 bytes, which is 2 to the 2. So we can fit 2 to the 11 pointers in a single indirect table. So if we want to calculate the number of blocks we can address with an inode, well, we can address 12 of them directly. So those are 12 direct pointers. Two to the 13 is the block size. So with our 12 direct pointers, we can point up to 12 blocks. And then for single indirect, well, it's one block. So we can point up to the 11 things. And then with a double indirect, well, that's 2 to the 11 to the power of 2, because each entry points to another one, which can hold 2 to the 11. And then similarly, for a triple indirect, it's 2 to the 11 to the power of 3. So instead of adding all these numbers, we can just guesstimate. So the biggest term here is going to be the last term. It is going to be by far the biggest, and it's pretty much going to be about that. So in actuality, you'll be able to support a bit more than this, but it's about that. So it's about 2 to the 11 to the power of 3, which we know how to do exponents. So that's 2 to the 13 things we can point to. So the total number of bytes that a file could be, well, we can have 2 to the 33 blocks, and each block is 2 to the 13. So if we multiply those together, we can support a file up to 2 to the 48, which is 64 terabytes. So that is what inodes use on Linux. So you can have a file up to 64 terabytes and a little bit bigger, because we didn't calculate these blocks, so it would be a bit bigger. But unfortunately, if you want to store a 70 terabyte file, you can't use an inode. So we haven't hit those limits yet, but one day. Okay, any questions about that? Yeah.
Sorry, so back to the inode structure, is the mode, is it user level kernel? Is that what that
Oh, no, sorry. So the mode here, the mode is like the same thing as your open, and it's the permissions of the file. So it's like read, write, execute. So when you do chmod some numbers, it's modifying the mode there. Yeah.
When you say indirect table, you're talking about single indirect, double indirect, and triple indirect, like number of entries within that, right?
Yeah, I'm just talking about how many things can fit on this. So if it's double indirect, I have 2 to the 11, and then each of them points to something that has 2 to the 11. And then if it's triple, it's another level. Yep.
So when you call open on like a very large file, what actually gets opened? Is it just like?
So you get a file descriptor to that file, so that when you read from it, it will actually start accessing the disk. But when you call open, you don't read from it, right? It just kind of sets everything up for you.
So as you start reading, it actually goes through this thing.
Yeah, so if there is a file on disk, your file is going to be represented by an inode. The first bit of information, the way to get to like the first byte of the file, it would have to access the first direct block and then see what that's pointing at, and then it would start reading that from disk, and that's the first byte of the file. So your kernel does that for you when you read, so it has to access this structure.
So then as you read it, like deeper and deeper into the file, you
Yep.
might get slower and slower.
Yeah.
More indirection.
Yeah. Yeah, so the point of this too is like usually you might only like read the first few bytes of a file and then decide you don't care about, so that's why it's also used the direct and you don't just straight up go to the like triple, even if it's a huge file. Yep.
So these are pointers to like blocks. So how would you actually like access the bytes of the data?
So if you want to access bytes of a data, well, the first byte is going to be on the first block.
Yeah, but like don't you need it to be byte accessible?
Yeah, so you can read in the block to memory from the disk, and then it's byte accessible. But with disks, typically you can only read them into memory at blocks at a time. And then you do byte accessible things. Okay, so let's see. So let's talk about hard links. So this might dispel some illusions you have. So actually, let's do this question. So who wants to tell me if I do something like, so if I do touch to-do.txt, so that will create a new file called to-do.txt that doesn't have any content on it, right? So, to-do.txt should reference an inode somehow, right? So if I do stat will tell me information about the file, and it's essentially stuff that is on the inode itself. So, but we'll see soon that this file is not stored in the inode itself, but all this information would be in the inode. So the size of the file, so it's 0 bytes, so it's empty. And then you can see, I'm not lying to you, it also says how many blocks it contains. So this one contains 0 blocks because it's empty. Then it says how big of a block is, and then what type it is, and where it is. And then here's the inode. So this is its inode number. So inodes are a real thing. And then there's this curious links number that we will look at soon. And then here's the access. So this is that mode parameter there. So sometimes they call it different things. In this, they call it access. Then, who owns the file, what group owns the file, and then all the timestamps here. So access, modify, change, and birth, which is just created. I don't know why they call it birth. And then we have ls, yep.
What's the difference between modify and change?
What's the difference between modified and change? I'm not sure. It's kind of weird, and some of the terminology is different. So usually it's just created, modified, and accessed. Don't ask me why this is slightly different. So if we do ls-l, there's some things we are kind of familiar with. So there's the modes there. This is actually the number of things that link to the file, and then who owns it, and timestamps and stuff like that. So soon we will explore that, how inodes connect to actual file names. So a hard link is just a pointer to an inode, and that is what to-do.txt is. So within a directory, all a directory is a pair of names to inodes, and that's it. That's all a directory contains. It's just a tuple, like a bunch of tuples of name to inode. That's it. There's no more discussion about that matter. That's all it is. Yep.
So is a directory itself a file with just file names in it?
So a directory itself, a directory itself is a special inode. So it's a directory inode. And the contents of that will be all of the name inode pairs. So there's actually not that much special about a directory. Yep.
So how do you translate from like a path to like an inode? Who does that?
How do you translate from a path to an inode?
Where do you go look up that information?
So you would go look up that information from the disk. So from the disk, there is a defined root inode, and that's how you know what inode that is. And the root inode is going to be a directory, so that's where all the names are. And then you just follow it through.
That has all the path and
Nope.
you have to
Yep. So yeah. The question is there a big table that just has all the files and all their paths? And the answer to that is no. All that are there's a special root directory, and that contains a bunch of names to inodes. And then past that, that root directory can contain other directories and other directories that have more names, so on and so forth. Yeah.
So you said it contains the file name and also the inode, like as like a.
So the file name and then what inode that file should represent, that name. So hard link points to one inode. So you can actually create multiple hard links. So what we can do is we can have to-do.txt, and then that would be assigned an inode. We got some long number for us. But we can also create another name that points to that. And then deleting a file doesn't actually delete the contents of an inode. It actually just removes a name, and that's all it does. So let's see that. So to
We copy a file from the C drive to your desktop, and when we delete the icon in desktop, doesn't actually delete the file.
Okay, let's go through the example first. So we'll talk about that. So in here, we have to-do.txt. It's empty. So I can create a hard link with just ln. So ln, so I'm going to create a new name that points to the same inode as todo.txt, and I'll call it b.txt. So when I create that, it looks like I have two files. And if I do ls-li, so this column is the inode column, and you can see that they both represent the exact same inode. So both names are the same inode, and then this number is the number of links to that inode. So now there's two things pointing to that inode. So what would happen if I edit todo.txt? I said hello, oops. So now I have todo.txt, our world's all right. So if I cat todo.txt, what am I going to see? Hello. What about if I cat b.txt? Yeah, because it's pointing to the same inode, so it's going to get the same contents of the file, because inodes just store all the blocks that file should represent. So I link them with ln. So all ln does is create a new entry in the directory that points to the same inode as the first argument. So now if I go ahead and I edit, b.txt, well, that's the same inode as hello. Or what I call it, todo.txt. So I'll edit b. So if I edit b, it's the same story. If I cat todo.txt, well, I actually changed the contents of the inode because I changed the data that is in the block. So now if I cat todo.txt, it's the same thing. It's the same content because it's the same underlying storage of that. All names are just ways of getting inodes. There's nothing else special about a name other than it's easier to type a name for you than to type an inode. You would probably be annoyed if you had to type, 1583612 every time you wanted to access that content. So, but other than that, there's nothing special about names. So, in addition to hard links, so if you called something a hard link instead of a link, that kind of gives you an idea that there's probably something called a soft link. So what a soft link is instead of pointing to an inode, it just points to another name. So it's kind of an additional layer of indirection. So this also leads to some interesting things. So if I have to resolve the file and b is a soft link to todo.txt, well, if I want to read that, I have to read b.txt, go figure out what b.txt it actually represents, and then use that to get the inode, and then I can actually finally read the contents of a file. So fun things about these are soft links are just contain a name that they're pointing to, so the name doesn't need to exist, which will give you some interesting errors. And even if it does exist at one point, the name it's pointing to might be deleted later, and unresolvable soft links will lead to some headaches. So some programs will automatically follow soft links for you, and some won't and will just refuse to run if they see a soft link. Yeah.
So if there's so many problems with soft links, what are the advantages over a hard link?
So the question is, if there's so many disadvantages with soft links, why do I use them for hard links instead of hard links? So you would use soft links. One, it's really easy to see what they're pointing to other than just like no one checks inode numbers. And number two is that they can actually break the strict hierarchy of things where you have to have directories within. So normally when we have a file system, we can't create giant loops, right? So with soft links, you can create loops if you want to, which is also why they're dangerous to go through.
So you could point a file to a directory?
Yeah, so a soft link just points to another name. It can be literally anywhere.
But it could be like another directory too.
Yep. Soft links just are to a name. Doesn't matter what that name is. Yeah.
Yeah, so in this case, I guess we would say b.txt is a soft link to do.txt.
Yep. Yeah.
That's,
Yep, that's it. Yeah.
So can you make like 3 soft links and have them point to each other?
Sure.
And what will happen when you try to like access one of them?
We can try that. we'll try. Yeah.
Are there any like common soft links in use like in today's like something on our computers or something like that?
Are there common soft links? So there's a lot of soft links. Typically, like real web servers will use soft links. It's typically you have files that represent, you know, a website. So typically, you might want to enable and disable a website. So instead of removing that file, you'll enable a site by just creating a soft link to that configuration. And then if you want to remove that file or remove that site from your web server, you just remove the soft link. So sometimes they're easier to deal with stuff like that, or just kind of rename stuff under the hood. So you might, you know, have a directory called Python with like the actual full version name. And you might create a soft link to that just called Python 3. And then if you update Python, that one would change, but you could still access it through Python 3 or something like that. So soft links are useful, but they're kind of a pain if you have to deal with them. Okay, so yeah, let's see an example problem and let's play around with it a little bit. So, oops. So we already have our hard link to, -li. So we already have our hard link to the same inode, so b and todo.txt point to the same thing. So I can create a soft link, and I will call, I will point to to.txt, I'll call it c.txt. So now when I look at it, well, I can see here is my symlink. So symlink's another way to say soft link. Typically, they're used interchangeably. So I've c.txt, and you can see it says it points to to-do.txt. And it itself is an inode. So there's an inode representing the symbolic link, and we can stat it if we want. So it says that the size of the file is 8, which makes sense. To-do.txt is 8 characters, so that's why its size is 8. And there's a special file type for symbolic links. So that's how the system knows what it is. Yep.
Why is it 0 block when there's the size of 8?
That is a great question. So there's a question is, why is it 0 blocks when the size is 8? So there is a optimization with symlinks. So typically symlinks are just going to be names, and they're going to be pretty short. So if I look, let's go back. If I look at all of my pointers here, so I'll have 12 direct blocks, 1 single, 1 double, and 1 triple. So I'll have 15 pointers here. Each pointer is 4 bytes. So the total of that is 60 bytes for all the pointers. So the optimization is if it's a symlink and the name it's pointing to is under 60 bytes, it will store the content on the pointers, because it knows if it's smaller than 60 bytes, I don't need to grab a block. I can just store the content in the inode itself. So for that case where to-do.txt is only size 8, well, it's just going to store itself in the block, in like the pointer data for the blocks. So there'll be 8 characters there, to-do.txt, and it will be living right like here and take up the space where 2 pointers would have been, since it's 8 characters. So that is a fun optimization, so we don't waste block size. Otherwise, how much internal fragmentation would we have if we just had an 8-character file? Right, it'd be 8 kilobytes minus 8 bytes. The rest of it, we're pretty much wasting 8 kilobytes. And then also the maximum length of a file name in a directory is 255 characters. So that is your limit on Linux. So there are limits to everything. Yeah.
So when you said like a directory is like a special inode,
Mm-hmm.
does it look similar or?
Yeah, so if it's a directory, the only difference, whoops, that's not. So if it's a directory, so we can just stat, actually dot's a directory, right? So dot is the current directory. So if I stat dot, you can see that it's just an inode too, but it's a directory inode.
Okay.
So nothing else special that, and its contents have some format, and the format is just name to inode. That's it. It's just a bunch of tuples.
Well, name is just the thing beside file, right?
Sorry?
Like the name is just file in colon, right? Like what's on the right side of that.
Oh, so the file is not stored, the file name itself is not stored on the inode itself. It's just pulling that from the argument I gave it.
Okay. But when you say like for a symbolic link, you say like the name, if it's less than 60 bytes, it will get stored directly on the inode.
Yep.
But what exactly is the name of the symbolic link? Is it just, in this case, stats
So in this case, it's just to-do.txt.
of the destination?
Yeah, it's the destination. So c.txt is going to be within the directory and then point to an inode, and whoops, dash I. So C points to this inode that has the 15. That inode is a symbolic link, and it contains that that to-do.txt. And that's, you can think of to-do.txt of the contents of that file. But it's defined that if that file type is symbolic link, the contents of the file is actually a name.
Wait, so it's only for symbolic links that we put data on the inode itself?
Yeah, that is an optimization only for symbolic links.
Okay. And is symbolic links like, is that like a soft link or?
Yeah, symbolic link and soft link are the exact same thing.
Okay.
It's just whoever, depends who you're talking to. Yeah.
So I noticed that for the c.txt, it's basically a soft link, right?
Yep.
And so its permissions are slightly different than what it's pointing to. So like, can user like tinker around and do things with that specific thing and not?
Yeah, so the question is the soft link permissions are it's all permissions. So all that means is you can read and write that soft link. It doesn't change the permissions to what it's pointing to. So even though it has all permissions, it doesn't mean, the group or anyone else can write to that file, because all the symlink would do is chase the name and then figure out, oh, I have to actually open the inode that to-do.txt points to. So now if I do this, if I cat c.txt, it kind of looks the same as all the rest of them. I'll see hello, I'll let it be. And this way they all kind of work the same way. And then next step I can do, they're all pointing to the same thing. Then we can see what move does. So move, funnily enough, does not move a single thing. So move is also another lie, and remove is a lie. So all move does is rename an entry in a directory if it's within the same directory. If you're moving it, it only actually moves if you move across directories. But if I'm within the same directory, I can move to-do.txt to something like d.txt. And if I ls again, well, I can see all I did, it's still pointing to the same inode. All I did was change the name. So now there's still two things pointing to that inode. I have d.txt and b.txt. But now you'll see something is in red because I broke the soft link. Yeah.
Sorry, why is there no red, like, why are there no arrows between B and D?
They're hard links.
Oh,
Yeah, B and D are hard links, so there's no arrow. The arrow is only for soft link, because soft link is just everything in directory is a name, and then if it's a soft link, it's name to another name, and then if it's a normal file, it's name to an inode. Yeah.
So b.txt, because it's a hard link, that is simply that simply has like the name and then the inode number, and then for c.txt, it contains the name and another name. Is that all?
Yeah, so in the directory, so if we went further and went into the directory, this directory would contain three names. The directory contains b.txt, c.txt, and d.txt. And then within them, b.txt is this inode, c.txt is this inode, which is actually a symlink, and then d.txt is this inode.
So that's Linux following the symlink, right?
Yeah, yeah, so ls, so this is ls following it. So ls will, if it's the file's a symlink, ls will display what it points to for you, because ls is nice like that. Yeah.
So when we do the ln call, it kind of points b.txt to the same inode as to do.txt.
Yeah, so the ln call, like without the -s, that creates a hard link, so it'll create a new name in the directory that points to the same inode as whatever the first argument is. Yeah.
Can you do the ln dash s to do to c and
Oh wait, c dot, other way around. So if I do that, it's smart enough to, they're both in red. So I just create a circular link there. So to-do.txt points to c.txt and to-do.txt points to c.txt, and it's smart enough. Smart. So
when there's a loop, it says it will actually give this error.
yeah, so this is probably something you haven't ever accounted for in your programs. Well, you guys probably never even think of handling a soft link, but in real programs, you have to handle soft links, so it's your choice. Do I follow it? And then if I do follow it, how many times do I follow it? So whoever wrote cat was a very smart cookie, because they stop after a certain level if you create an infinite loop. But this is the power of symlinks or soft links. I can create an infinite loop, but with normal files, I can't. I'm not allowed to.
So cat actually tried to do it.
Yep. So cat tried to do it, and it said too many levels. So I followed. It's going to have a limit where it will follow symlinks to, I don't know, whatever number. Probably something sane, like, I don't know, what's a sane number? Like 8 would be kind of insane too. But it'd be like some low number, because otherwise it gets kind of crazy.
So you can only have like 8 links.
Yeah, whoever wrote cat, it follows it a specified number of times, and if it can't actually find a real file, it gives up. So cat is a bit smarter than us. But that was a cool thing to do. All right, so where are we? Yeah.
So you said that you could, like with the soft link, you could connect it to any of, like say you wanted to connect it like to a file outside of this directory. How do you?
Yeah, you can.
To give it the whole path. Like, what, do you have to give it the name or
Yeah,
the full path?
yeah, you can give it whatever name you want. So the first argument is actually a path. So I could do whatever. I could do dot 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 dot. I don't know. It doesn't even need to exist. Like hi. Whoops, I didn't call it anything.
So what if there is a quote-unquote real file in between?
Sorry?
Like let's say you have your C that's linked to D, but D is linked to C. Like what will happen then?
For the
Because they're both still technically real files with content, right?
C is linked to D, sorry?
Like let's suppose we have like file C that has a soft link with file D, but D also has a link to file C. But like would that cause an issue?
That's what we just did. That's like a circular loop.
Yeah, but in this case, you said it was like with the other one, the symbolic links, they're like fake files and stuff.
Yeah, so it just follows them. But
in this case, like D and C are real files.
But then if they're real files, it's just going to read that inode, whatever's on that inode. It's done.
Oh, okay.
So it doesn't carry.
Loops only occur when it's like you're pointing a symbolic link to a symbolic link to a symbolic link.
Yeah. Or, well, I can create a loop if the symbolic link just goes up and then I follow it to myself again. So you can create some recursive cases with it. Yeah.
Where are like paths and then names kind of resolved? Like if I put in like just to-do.txt, that resolves to like a specific inode because I'm in this directory.
Mm-hmm.
But if I was outside of it, I would need to give it the full path of it. So like where does that, like where does those match up? Because they both point to the same thing. How does like that come back?
So this, like if I do this, or wherever it is, was it? Like this?
Yeah. Like how do those things get resolved to be the same?
So how do these things resolve to be the same? So it will follow it first. The only real trick to it is there is a special named inode for the root directory. So if you do a path like this, it knows what the root inode is. And spoiler alert, it's inode 2, I think. I'm pretty sure it's inode 2. So it knows to go to inode 2, and then within inode 2, it will look for the name called home inside that directory, because it will be a directory.
Directory inode, right?
Yeah, like the root inode is a directory inode. So within that, there'll be a bunch of names to other inodes. So there would be, in the root directory one, there would be a entry called home, and it would point to an inode, and that inode would also be a directory. So I would go in that directory, and within that directory, there'd be an entry called John, which would point to an inode that is, and again, another directory. And then within that directory, you know, we can see where this is going. There's something called examples. I'd follow it, so you just have to go all the way through. And then for relatives pass, well, that's why there's a dot here. So since there's a dot, I mean, you can just get the inode for the current directory, and you know it's a directory inode, so you can figure it out.
I see. Was it technically faster to do that one because you're only like doing the levels from this point on than actually from all the way from root? Because technically you have to trace back to all that.
Yeah, technically it'd be faster to do relative paths because you don't have to start root, unless you go all the way back and then all the way forward. Okay, so that. Oh, yeah, and then we can do a fun thing called RM. So RM, we'll see that doesn't actually delete anything. So we have two things pointing to the same inode. If I remove b.txt, well, didn't delete anything because we know b.txt and d.txt are the same content and the same actual file. And it's still there, it's not deleted because there's still one reference to that inode. So if we stat it again, we see that the number of links has decreased. It was 2 because 2 things point to it, and now 1 thing points to it. So that inode will only be reclaimed and reused again if 0 things point to it and will actually get deleted. So RM doesn't actually remove anything. All it actually removes is that name in the directory. So it just removes that entry for the name in the directory. That's it. If it's the last reference to the inode, it might get deleted, but that's up to the kernel, and it probably won't. Okay, so quickly, because we have TA evaluations we need to fill in as well. So after all of this, it looks like this, where c.txt points to points to the name to-do.txt, which doesn't actually exist, so I'll put in a black background. And then d.txt points to an inode that actually represents the original to-do.txt. But to-do.txt has long been removed. So Linux, everything's a file. So directories are also inodes, so we kind of saw that. So the only difference is that their file type is a directory, and then there is a special format that says, you know, it has to contain name to inode. And the names, again, maximum size is 255 bytes. So you can create a path that's huge, but each individual name is only 255 bytes. So other things they can be, there's regular files, there's block devices. So even your hard drives will be represented by a file. And a block device just means you can't access them byte by byte. You have to access them in big blocks. Yep.
Wait, does that mean that the max size for a hard drive is the 64 terabyte if they're represented by an inode? Didn't you say like inodes have a maximum size of 64 terabytes?
No, so that's, an inode represents a file.
Didn't you say a block device is a file?
Yeah, so it represents a block device, but it's just its representation. There's other ways to represent block device so I can access the whole thing.
Okay.
Yeah, so directory inodes don't do anything that special. All they contain is name to inode. That's it. So we'll go through this quick. What's stored in an inode? So the file name is not stored in an inode. The names only exist in a directory. That's the only place names exist. And then inodes also do not know what containing directory they're in. They have no idea whatsoever. You have to follow all the links to figure out where it is. There's no back mapping or anything like that. They do contain the file size, so it's whatever it represents. They contain the file type, so regular file, symbolic link, or directory are the main ones you'll probably encounter. If an inode's a soft link, or just an inode doesn't even know how many soft links are pointing to it, doesn't know where the location is. It, however, does know the number of hard links to it, so that was one of the things that are stored on it, so the kernel knows if it can actually delete what it points to. And then the location of hard links it doesn't know, and then other things it stores the access, timestamps, and file contents sometimes, so that's that gotcha thing. So if it is a small symbolic link, the inode will actually contain the contents of that. Yeah.
So for the file names, I know like regular file inodes won't, but like a directory inode does contain the file. I'm just kind of confused about this.
No, so a directory name doesn't contain any other, doesn't contain its own name.
No, I know, but like it would contain the names of the files within it, right?
Yes.
Okay.
Yeah, which would be the contents of that inode, but not the inode itself.
I see, okay.
Yeah, and then by definition, an inode will store an ordered list of data blocks. So one thing too is we saw using caches to speed up write. So writes are slow, we can use a cache. So you could also cache a file system. So there'd be a file system cache. And sometimes you might want to bring in stuff ahead of time. That's like the prefetching thing that Windows might do. So if you're referencing a block, you might want to reference it again if it represents a database. So I'll keep it in memory instead of writing it back and forth to disk. And then sometimes you'll read a file sequentially, so maybe I just read it into memory ahead of time before you do it, so it's already there by the time you get it. And then the kernel is responsible for actually writing the changes back to the disk, and we saw that before with the write-through stuff. And then the way to control that there are system calls for flush and sync, and that will trigger the kernel to actually write data, clear all the caches, and actually write it to disk. So that's what they do. All right. Last thing quick is the journaling file system. So deleting a file it's like a 3-step process. So to actually delete the contents of a file, it would have to remove its directory entry. And then assuming that that's the last link to the inode, it would have to release the inode to the pool of free inodes. And then also record that all those disk blocks that inode points to are now free, and they would be a bitmap, so they would have to zero them out. So if you care about data integrity, your power could go out at any point in this process. So if my power goes out between 1 and 2, well, I'm not going to have any way to access the directory or inode through names anymore, but it's going to look like it is still in use, and all the disk blocks it's using are going to look like they're in use. And then if I crash between step 2 and 3, well, that inode's not even going to exist anymore, but all the blocks it was pointing to are going to be used, and I can never reuse them again. Yeah.
So in a directory type file, the inode contains pointer to other inodes.
So in the directory type, the contents of that inode, so the blocks it points to, the data that it points to are going to just be name inode pairs.
Right, okay. Or name, and then
Huh?
Or name name, right?
No, always name inode.
What about soft links?
So inode's a soft link is an inode. There's an inode soft link.
But doesn't the directory contain the...
Nope. So the directory does contain the soft link, but here, if we look, so this is a soft link, right? But whoops, that is not, it crashed, cool. Yeah, so it is an inode. So the soft link is itself an inode, and the only way we see to do .txt is because ls actually grabs the content of it. So if we look at it, itself is an inode, and its type is symbolic link. So directory doesn't change name to inode.
Okay.
Yeah.
can files share the same disk block?
They shouldn't.
They should.
Yeah. All right, yeah, so last thing, journal. basically it just writes what things are going to happen. So if it crashes, so it would write what it's about to do. And then if it crashes anywhere in step 1, 2, or 3, that entry would still be in the journal, so it knows where it needs to go look for to actually recover all that data and go through. And it can figure out where it crashed from there and then make everything consistent. And then the usual case for a journal is once it's done all the steps, it would go ahead and remove itself from the journal, and then you know it's all consistent. So that's it. I guess there's office hours now, and if you can, there's a TA thing. So just remember, pulling for you, we're all in this